Okay, where we left off last time, we had been discussing the orbitals in H2. H2 is really the simplest example of a molecule you can describe with molecular orbitals. And we said one rule of orbitals is when you combine two atomic orbitals, you have to get two molecular orbitals out. So we combined them once in phase, and we made a bonding orbital. And we combined them once out of phase and made an antibonding orbital. I didn't get a chance to elaborate on the antibonding orbital. So, first of all, why is this antibonding? Well, remember, you have the nuclei, which are positively charged. And then you have electron density on the two outsides. So if you're the nuclei, which way are you getting pulled by that electron density? Out, right? Nuclei are pulled out. So, hence the term antibonding. The other thing to note here is, in terms of potential energy, electrons are at lowest potential energy when they get to be close to positive charges, close to nuclei. So, as compared to the atomic orbitals, the electrons in the antibonding orbital are actually further apart from the nuclei than they otherwise would be. So what does that mean about their potential energy? Higher. So the antibonding orbital has higher potential energy than the atomic orbitals. So what we have is two atomic orbitals. They come together, they make two molecular orbitals. And now I'm going to show you the conventional way to represent this. We call it a splitting diagram. All right. In a splitting diagram, you represent atomic orbitals on the outside. Well, so I would put H and H on the two sides. And then in the middle, you represent the molecular orbitals. And the way we represent orbitals is actually really simple. We just draw a line, a short little horizontal line, and label it with the orbital type. So, for the two hydrogen atoms, I'm just going to draw a little horizontal line for each one. What orbital does the hydrogen atom have? 1s, so I'm just going to label that 1s. So we put those on the outside. And then in the middle, I'm going to represent the two molecular orbitals. One of the molecular orbitals we made, and this vertical axis represents energy. So one of the molecular orbitals we made was the bonding orbital. Was that lower or higher in energy than the atomic orbitals? Bonding orbital was lower, antibonding was higher. So in the middle for H2 I'll have one that's higher up, one that's lower. The bonding orbital we called sigma. The antibonding orbital we called sigma star. Just a note, we put a little asterisk and we say star when we're saying the name of that orbital. So that would be called sigma star. And then we just put little dotted lines to show where the molecular orbitals came from. So this bonding orbital came partly from the 1s of the first hydrogen atom, partly from the 1s of the second hydrogen atom. And the sigma star also came from those two orbitals. And then we represent electrons with the little arrows. That point up or down. This comes out of quantum mechanics and this thing we call spin. It's not really that important other than for you to know that each orbital can hold up to 2 electrons. One of them would be pointed up and one of them would be pointed down. So we start with the 2 hydrogen atoms. Individually, they each had 1 electron. When they come together, they make this bonding orbital and this anti-bonding orbital. Now, if you were those 2 electrons, which orbital would you rather go in? If you're these electrons, would you rather be in the anti-bonding orbital or the bonding orbital? The bonding orbital. So both electrons go in that bonding orbital. So one key thing to note is that the electrons are now at lower energy than they were in the individual atoms. So the question is, why do they go in the lower energy one? And the answer is, well, electrons always want to go into the lowest energy orbital possible. If you go back to your first year of chemistry and you talk about electron configuration, you always fill from the bottom up because electrons will go to the lowest potential energy they can. So in H2, they're at lower potential energy than they were in the 2 separate H atoms. That's another way of saying H2 is more stable than 2 individual H atoms. So this is really just another way to describe the bonding in atoms and describe why the electrons are happier to be in the 2 bonded atoms than they were to be in separate atoms. So when we talk about a molecular orbital splitting diagram, we mean a diagram like this. The dotted lines there that I'll highlight again in green. These dotted lines represent what we call, what we sometimes call parentage, meaning the atomic orbitals are like the parents from which the molecular orbitals were made. So the dotted lines represent which atomic orbitals went into making which molecular orbitals. And if you take a general chemistry class in college, your first year, they might do some more complicated molecular orbital diagrams than we're going to do. We're going to stick with pretty simple representations, and we're not usually going to draw these splitting diagrams. Usually we're going to ignore the 2 sides and just draw the middle. But you will see those dotted lines in future courses. All right, any questions about what we just drew? All right. So this is just a summary. When we overlap two orbitals, we combine them twice. We combine them once in phase and once out of phase. When we combine them in phase, we made a bonding orbital that had high electron density between the two nuclei, so it pulls the nuclei together. And if you're watching this, you don't necessarily need to copy all this down because these are all things that are written on the previous slides. But if you want to have a summary in one place, then you can copy it. So you make a bonding orbital that pulls the nuclei together. The potential energy is lower than the parent atomic orbitals. And when you overlap them out of phase, you make an antibonding orbital where the electron density is low between the two nuclei. So electrons in an antibonding orbital would pull the nuclei apart, and the potential energy for the antibonding orbital is higher than it was for the parents. I'm going to wait for the people in the room to copy that, but feel free to fast forward if you're watching this and you've already copied it. All right, so the question is, do in-phase and out-of-phase both happen when they overlap? And the answer is yes. So every time we create a bonding orbital, we're going to create a corresponding antibonding orbital. In more complicated formulations of molecular orbital theory, you would it wouldn't be so clear-cut what's bonding and what's antibonding, and you actually involve lots of orbitals in one molecular orbital. But for us, we're going to treat it as if each MO comes from just two atomic orbitals, and so they always are going to come in these bonding and antibonding pairs. You may see more complicated formulations that do, that get a little wilder, but we're not going to do them. All right, so let's consider CH4. If we wanted to draw a diagram for CH4, we would first consider, what does CH4 look like? Well, it's carbon with 4 sigma bonds. What's the first thing you would want to know about the orbitals in carbon in that molecule? What can you tell me about the atomic orbitals in carbon in the CH4 molecule? It would be sp3 hybridized. Yep. So that would mean carbon has 4 sp3 hybrid orbitals, so I draw 4 little lines. And then hydrogen, well, there's 4 of them, and each of them has a 1s orbital. So I draw 4 little lines there. All right, so the question is, did I draw them at different heights on purpose? Yes, I did. Maybe I didn't need to make them at such different heights, although they're still pretty close. I did. We'll talk about that in a minute, but different kinds of atoms have different energies for their orbitals. For us, the simple proxy for orbital energy is going to be electronegativity. More electronegative atoms will have lower energy orbitals. Less electronegative atoms will have higher energy orbitals. I'll talk more about that in a minute. But for our purposes at this point, it doesn't necessarily matter all that much what exactly what height we draw those two at. So let's consider just one of the bonds, and let's imagine what the bonding and anti-bonding orbitals would look like. So if I imagine CH, C and H bonding, carbon's got an sp3 hybrid orbital, which would look like this. Hydrogen's got a 1s orbital, which would look like that. So if I combine those two orbitals, right now have I drawn them in phase or out of phase? How do you know it's in phase? They overlap and they're both unshaded where they're overlapping. So when I do this, I would make a bonding orbital. And that bonding orbital, we'll call this sigma CH. That bonding orbital is going to have a tiny part here and then kind of a big part between the two atoms. And we're going to do that 4 times. So there'd be 4 of those. So I would make 4 sigma CH orbitals. I could also combine them out of phase. So I could put them together like that. That's going to make an antibonding orbital. So if I put those together, now what's going to happen is I'm going to get a bigger part out here, tiny part in the middle, and then a bigger part out here. We would call that sigma star CH. And that's going to happen 4 times. So I'll have 4 of those. All right, so the question is, do I have this right? Both the in phase and out of phase exist. We make the bonding orbitals and the antibonding orbitals, but only the bonding orbitals have electrons in them. And in our simplified model, yes, that's going to be the case. Like I said, you will, in the future, probably encounter situations where antibonding orbitals do get filled, but for us, they're never going to get filled. Because if we count our electrons, how many valence electrons does carbon have? 4. So carbon would have 1, 2, 3, 4 electrons. And how many electrons does each hydrogen have? 1. So 1 from each hydrogen is going to be 4 more. So then I have 8. So I have just enough to fill up all the bonding orbitals and leave the antibonding orbitals empty. And, you know, the next logical question might be, well, if the antibonding orbitals never have electrons in them, you know, how do we know they exist? And why do we care? So my response is, we don't know any of this exists. This is all just a model. What makes a model useful is if it makes good predictions. And I will show you, maybe not today, but next time, hopefully, I will show you how this model makes good predictions. And the antibonding orbitals play a vital role in making good predictions. So, for now, you just have to imagine, okay, they're there, or I can at least pretend that they're there, and that'll help us make predictions. All right, so this is what a splitting diagram for CH4 might look like. Any other questions? All right. So then, what if I throw in a more electronegative atom? All right. So let's say I take CH3Cl. This molecule has two things going on that the prior examples didn't. Number one, it has an atom with a much different electronegativity. And number two, it has lone pairs. So the question is, how do I deal with those two things? Well, what I'm going to do is I'm not going to draw a single splitting diagram for the whole thing. Once we get past simple examples like H2 or CH4, I'm really not going to draw a single splitting diagram that shows a whole molecule anymore. But we can consider each individual bond. So this is going to kind of go back to Module 5 where we're describing all the bonds in a molecule. First of all, once again, we'd say carbon has what hybridization here? sp3. And what hybridization does chlorine have? Also sp3. All right. So if I consider the carbon and the chlorine, I'll call this a partial splitting diagram. For carbon and chlorine. Chlorine's got these 4 sp3 hybrid orbitals. Now, if you're an electron, who are you more attracted to, carbon or chlorine? Chlorine. Chlorine's a lot more electronegative. So chlorine's orbitals are going to start out a lot lower energy than carbon's orbitals. Now, how many of the carbon sp3 orbitals are actually overlapping with a chlorine orbital? Only one of them. So, really, I'm going to ignore these. I'm going to ignore 3 of them. For now, because they don't overlap with the chlorine. But I know that I have one carbon sp3 orbital that overlaps with one of the chlorine sp3 orbitals. So that's going to make a bonding orbital that I'm going to call sigma CCl. And it's going to make an antibonding orbital that I'm going to call sigma star CCl. So just like we said before, anytime we make a bond, we're going to make a bonding orbital and an antibonding orbital. But the point I want to make here is that the bonding orbital is closer in energy to the chlorine atomic orbital that it came from. It turns out that means that that molecular orbital will look more like the chlorine atomic orbital, or it'll lie more on the chlorine than it does on the carbon. All right. So this is closer to chlorine than carbon. Whereas the antibonding orbital is going to be closer to carbon than to chlorine. What that means is if I were to draw these two orbitals, and I think I'm going to have to add space that I didn't include earlier. That means is if I want to draw sigma CCl, really that's going to come from the sp orbital on one overlapping in phase with the sp orbital on the other. If this is carbon and this is chlorine, the bonding orbital is going to come more from the chlorine side than from the carbon side. So what it looks like is going to be a little more pear-shaped and have a little bit more electron density close to the chlorine. Now that makes sense with our, our prior description of bonding, because we would have said a carbon-chlorine bond is polar. And what does it mean to say that the carbon-chlorine bond is polar? Come on, you know what that means. What does it mean when I say the carbon-chlorine bond is polar? They don't share the electrons equally. The electrons are pulled closer to chlorine. And our picture of the bonding orbital, as inaccurate as this may be, if we were to actually do if I were to simulate this with a program that actually does the quantum mechanical approximations, it might not look exactly like that. But the idea is the electrons get pulled closer to chlorine than they do to carbon. The other side of that, the flip side, is that if I want to see sigma star CCl, I have my carbon orbital and my chlorine orbital. Now the sigma star is going to have a greater contribution from carbon and a smaller contribution from chlorine. And so if they come together out of phase like that, my sigma star orbital is going to have a big lobe on carbon and a smaller lobe on chlorine. No, this is carbon, this is chlorine. So the bonding orbital lies closer to chlorine. The antibonding orbital lies more on carbon. And again, that's going to have repercussions in terms of reactivity. All right, so going back to this splitting diagram that I drew. I just considered the sp3 orbital from each atom overlapping with each other. That made a bonding orbital and an antibonding orbital. 2 electrons would go into that bonding orbital. I outlined in blue these 3 other sp3 orbitals from carbon that I said those overlap with hydrogen, not chlorine. What about the other 3 orbitals on chlorine? What do they overlap with? Nothing. So what happens to their energy? It stays. So what will happen with these 3 orbitals? Chlorine has 7 valence electrons, so these 3 orbitals were filled. They just stay right where they are. They're not bonding. They're not antibonding. What do you think we call them? We call them non-bonding. Just a lowercase n. You can call them lowercase n Cl. N equals non-bonding. Another way to designate them would just be to say chlorine lone pairs. So sometimes you'll see them just called ClLP for chlorine lone pair. But when you have orbitals that don't overlap with anything, those just stay right in the middle. All right, so far I've only considered the carbon and the chlorine. I ignored the hydrogens because it's kind of a pain to put all that in one splitting diagram. This is why we're going to move from drawing splitting diagrams to just drawing what's in the middle. All right. So far, my molecular orbitals I'll call it H3CCl. So far, the molecular orbitals I have are sigma CCl. I have sigma star CCl. I have the chlorine non-bonding. and there were 3 of those. What other orbitals am I going to need to include in my diagram? What haven't I considered yet? The CH orbitals. Those 3 sp3 orbitals from carbon that overlap with hydrogen 1s orbitals, those are going to go and make sigma CH and sigma star CH like we've seen before. So the question is, where do those end up in the diagram? Well, since hydrogen is not as electronegative as chlorine, hydrogen's orbitals don't start as low in energy as chlorine's do. And so the bonding orbitals and the antibonding orbitals that it makes won't end up as low in energy. So in other words, I already have these. I also am going to have my carbon and hydrogen. I'm going to have to superimpose sigma CH and sigma star CH. I'm going to have to put those in here somewhere. And it turns out they go right here. Oops. So the sigma CH aren't as low in energy as sigma star CCl, as sigma CCl, because hydrogen is not as electronegative as chlorine. Sigma star CH is not as low in energy as sigma star CCl, because hydrogen is not as electronegative as chlorine. And then my bonding orbitals are going to be filled. My lone pairs are filled with electrons. And then my antibonding orbitals are empty. So from now on, rather than doing splitting diagrams, all we're going to do is draw the orbitals that would be in the middle, the molecular orbitals. We're going to ignore the atomic orbitals that they come from, because it just will make our diagrams too much of a mess. What questions do you have? So at this point, I'm going to go back and check. Let me make sure I have the right number of orbitals. All right. It was CH3Cl. Carbon has 4 orbitals. Cl has 4 orbitals. 3 H's have a total of how many orbitals? So I should have in my diagram 11 orbitals represented. So remember that rule. Whatever number of orbitals you start with has to be the same as the number of orbitals you end with. So I look at my diagram. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 orbitals represented. Great. I also should have the right number of valence electrons. For that, I can look at the Lewis structure. The Lewis structure had 1, 2, 3, 4 bonds and 3 lone pairs. I look at my diagram, so that's a total of 7 pairs of electrons, and I have 7 pairs of electrons in my diagram. So the question is, are there ever going to be electrons in the star, in the antibonding orbitals? And my response is not in this class. Not with the technique we're going to use. That's not to say you won't see such a thing in other courses. But with the simplified technique we're using, sigma star orbitals are always going to be empty. All right. So to summarize, electronegativity, the way it affects orbital energy. More electronegative atoms have lower energy. Lower energy orbitals. The energy of bonding or antibonding orbitals, or the relative energy of bonding and antibonding orbitals, will be based on the sum of the electronegativity of the two atoms involved. So, for example, sigma CCl, we said was lower energy than sigma CH. Sigma NO would be lower than sigma Cn, for example. And that's because oxygen's more electronegative than carbon. All right, so actually I gave myself this slide, but I did this earlier, so I don't need to use that slide. What we did is we looked at the CCl bond, and we said the bonding orbital looks more like the more electronegative parent. The antibonding orbital lies more on the less electronegative atom. All right, so I'm going to give you this challenge right now. Try and draw the molecular orbital diagram for CH2ClF, meaning this molecule. And we're abandoning doing the splitting diagram now. We're just thinking about what orbitals do I need to include in my diagram. So looking at this Lewis structure, what orbitals do I know have to be there? All right, I need a CF bond. And if I have a CF bond, I also need a CF antibonding orbital. All right, what else? I need a CCl bond, CCl antibonding. What else do I need? Lone pairs. I need 3 non-bonding orbitals on chlorine and 3 non-bonding orbitals on fluorine. And what else? I need 2 sigma CH bonds and 2 sigma star CH orbitals. All right, so try and draw a molecular orbital diagram that includes all those in the right energy order. So broadly speaking, you're breaking your diagram into 3 different parts: bonding, non-bonding, and antibonding. And then within each group, you're arranging them by electronegativity. So within the bonding group, what's the lowest energy orbital? Sigma CF. And then sigma CCl. And then we have our 2 sigma CHs. Then for my non-bonding orbitals, F would be lower than Cl. Then for antibonding, this is where it throws people because people like symmetry. And so people often want to do like the reverse order on top that they had on the bottom, but it's not. The lowest energy one would be sigma star CF, followed by sigma star CCl, and then sigma star CH. And then for electrons, I would fill them in from the bottom up. All right. So there we have our molecular orbital diagram. There's only one more real wrinkle that we're going to throw into these. What's the one thing we haven't considered yet? Pi bonding. Yeah. So the only other wrinkle that'll get thrown into these will be pi bonding. And it's not that bad. But I think I'll save that for next time.